Hey everyone, I'm Nick from Coffee Before Art, and today we're going to be talking about coherence basics. So in the last episode of this series, we talked about what the basics of memory consistency actually mean, and then also what we really meant by cache coherence. So we need to really kind of dive a little deeper than the example of a classroom number being changed on a website, and present a more realistic scenario, as well as the system that is going to be the basis for all the examples that we're going to go through. So as always, we need to preface this as we're going to introduce cache coherence and understand how the consistency models interact with caches. So just as a little reminder, the coherence protocol that we implement is simply a mechanism to help us attain whatever our memory consistency model is. It's not a prerequisite to having a memory consistency model. So, we're going to talk about a couple things. So we need to talk about first, the system that we're going to be using as the basis for all of our work. Then we need to talk about, what is the cache coherence problem and present it in, kind of a new light, as well as, a little more precisely defining what we mean by cache coherence and what we're really striving for in this baseline system. So, so what is our baseline system, right? So we need to, of course, set this up. So it's going to be a fairly simple system, but it'll be comprehensive enough to really, build these ideas into. So again, when we're talking about cache coherence and memory consistency, what we're really concerned about is multi-core stuff. So we care about sharing, and so we generally have concurrent sharing is the problem, and we really get this, and this has really come around a lot more now that pretty much every CPU nowadays in a commercial part is a multi-core processor chip with off-chip main memory. So we'll consider this this scenario where we've got a multi-processor chip, and we've got a multi-core processor chip, and then each of the cores are they have some number of multi-threaded cores. The exact number doesn't really matter. That's more of a scaling issue. So we'll also assume that each of these cores has their own private data cache, as well as a shared last level cache that all cores are connected to. So again, this is like having a private L1 cache and then a shared L2 cache. So each core's data cache is going to be accessed with physical addresses and is write back. So what we mean by this is that by write back is that the values aren't immediately written back to main memory. They're going to stick around in the caches until, say, they get evicted, right? So this really is where the coherence problem starts to take form a little more, because we don't have memory always being updated. It's going to get stale at some parts, and by stale I mean there'll be a newer value in the cache that isn't present in memory. Okay, so then the cores in LLC communicate with each other over an interconnection network. So the exact details of that don't matter, although it is a big part of ensuring coherence is understanding interconnection networks, but that's kind of out of the scope of this series. So despite the LLC being on the processor chip, logically it's a memory side cache, and that's because everybody tunnels in and connects to the same cache. So it's essentially an extension of the memory system, or it's an extension of main memory. Okay, so let's go ahead and look at this. So here's our cores. So each of these cores on this single multi-core processor chip, this will have one thread running on each of these cores, and then we can have n of them. The amount, like we said, the number of cores is more of a scaling issue that will determine things like how our buses or interconnection networks actually work, or these designs, but we're going to ignore that for now. So we'll just assume we have n cores, each of which have a private data cache that we'll just call maybe an L1 cache. And then everybody connects through this interconnection network to our last level cache / memory controller. And so here's our last level cache. So this will basically be our shared L2 cache. And then of course we've got off chip main memory. So everything up here is on chip, everything over here is off chip. Okay, So let's talk about how we actually get incoherent situations. And really where this comes from is, just simply by having multiple actors with accesses to cache and memory. So in our case, we're talking about each of the different threads that belong in a different core as an individual actor. In reality, it's more complicated than this. As always, reality tends to bring on new problems. So we could have, DMA engines, so this is direct memory access engines, or external devices that can read or write to caches in memory. But, these are really just extensions. So we could essentially think of these things as, other cores that are going to be interacting with the memory system. There's a little more, there's a little more complication than that, but again, fundamentally some of the concepts are the same. But again, we're going to focus on this baseline system. So let's actually go through an example and see where incoherence come from. So we'll start with some assembly instructions, and this is a simple 2-core system, right? So we'll take this as, say, for n cores, n equals 2 in this case. So let's say that core 1 executes an instruction that's just a load. So this is just loading a value from main memory into R1. So it's going to issue this request. It's going to go down through the memory system. It's going to find this value in memory, and it'll load it up through the memory system, and we'll get a request, and then eventually it will get put into the cache. This again is going to be like the L1 cache, which again is private. So nothing wrong at this point. We can of course cache values. Caches are an essential part of helping performance and helping hide and exploit locality to help pretend like our memory system is much faster than it is in reality, or that main memory is in reality. And then core 2, maybe at some point later on, it issues a load of its own. And again, there's still no problem at this point. So in systems where we have only reads, there actually is no problem, right? Because the data is still the same everywhere. So again, this value comes into memory. It's the exact same as the value in core 1, which is also going to be, if we had some black box around here that's actually main memory, all 3 of these values are going to be exactly the same. So we've got no problem at this point. But we generally don't read values just for fun. We generally read values because we want to do something to them. So in this case, we'll do 2 instructions. So over here, we'll go ahead and add, say, the value 1 to R1, right? And then we'll store this value back to memory. So we'll update, we'll hit and say our L1 data cache, and we'll update this value inside of this L1 cache, right? So again, these are write back caches, not write through caches. So we don't write this value back to main memory right away. It's actually just going to stay here. So what's the problem at this point? So the problem is that different cores think that this memory location A, has a different value, right? So at this point, by the time we do a store, caches aren't supposed to enable new functionality. They're supposed to really just make it seem like our memory system or our main memory is a lot faster than it is in reality by exploiting locality. But in this case, that's not what it's doing. So A over here, which represents just a memory address, is equal to 43. But the exact same value of A over here, the exact same address to memory, is 42, right? So 2 different values for the same piece of memory. So that's incoherence. This is the problem that we want to get rid of, or that we want to address, right, with cache coherence. So of course, this is a very hand wavy type example. It's very intuitively incorrect. So we don't want to do everything based upon intuition, though. So we want to create a more precise definition of what incoherence means. So typically when we're talking about coherence, the preferred definition that most people go by is this idea of having single writer, multiple reader invariant. So that means that for any given memory location, so coherence deals with a single memory location, right? So and this will be for every single memory location you'll have coherence for. But coherence itself is really just focused on what's happening at a single memory location. So for any given memory location, at any given moment in time, there is either a single core that may write to it, and of course if you can write to it, this also implies that you can read to it, or some number of cores that may read it. Now, the number of cores that may read it may also be 0, right? So both of these could be 0. So, you could have a situation where there's just not a cache block in anybody's cache. So in that case, nobody's reading it, nobody's writing it. But it's saying that specifically, we can only have one writer at a time, or some number of cores, doesn't have to be any cores, can read it, but multiple can read it if they can read it. So again, there's never any time where a given memory location may be written by more than one core simultaneously. And as well, if somebody's writing, somebody else can't read. So we'll see how we can kind of address this. So another way to define that is basically through this idea of epoch. So this is kind of a rough conceptual, like time kind of view. So again, core 2 and 5, they can be readers at this moment. As soon as core 3 over here wants to write, it gets read-write permissions, but it's the only person with read-write permission. So as soon as this core wants to write, it ends this read-only epoch. And then as soon as another core wants to write, it ends this core 3's read-write epoch. Then over here, say core 2 and 3 want to read now. So it ends core 1's read-write epoch, and then all of a sudden cores 1, 2, and 3 all enter a read-only epoch, because again, single writer, multiple reader. Okay. So, there's other interpretations that are basically the same, that just use slightly different ways of saying this. So one of the ways that that sometimes people describe it is through tokens, right? So there's a fixed number of tokens in the system that's at least as large as the number of cores. So you can think of every core getting a token. So if a core wants to write a memory location, they've got to collect all the tokens from everybody else. If a core wants to read a token, they have to have at least one token. So that's just kind of an alternative way of saying, single writer, multiple reader. Okay, and that's this definition here, right? So we've got two things that we want to make sure happen. We want to make sure that for any memory location A, at any given logical time, there exists only a single core that may write and can also read it, or some number of cores that may also read A, which could also be equal to 0. So then there's the data value invariant. So that really ties a little better to the epoch side of things. So the value of a memory location at the start of an epoch is the same as the value of a memory location at the end of the last read-write epoch. So let's look at the read-write epochs here. So here we have our first read-write epoch with core 3. And then all this is saying is that when this core 1 wants to do a read-write, it should have the value produced by core 3. Same thing here. As soon as we want to transition from this read-write epoch to this read-only epoch, cores 1, 2, and 3 should have this value. So it's really just a way of saying that whenever we end an epoch, everybody that is, say, an actor or doing something, whether they're reading or writing, should have the most recent value. Okay. So, how do we handle this, right? So, we've kind of talked about how we define cache coherence and what that means, but how do we maintain this idea of, having the most recent value be seen by everybody and making sure that there's only going to be a single writer at a time? So most of the coherence protocols that exist today are considered invalidate protocols, and they're designed explicitly to maintain these two invariants, so the data value invariant and the single writer multiple reader invariant. So, if a core wants to read a memory location, it has to send messages to other cores to get the latest value of a memory location. So in this case, okay, I I'm doing a load, right? I want a load value of A. So the first thing I need to do is I need to talk to all the other cores, right? Because the other cores could have been a writer, right? And in that case, memory is going to be stale because the most recent value is actually in somebody else's cache. So what I should do is I should, ask everybody, hey, do you have a more recent value? If nobody replies, then I've got to go to memory and fetch it, because that means that the memory has the most recent value. If not, I have to be able to get it from the cache. Okay, so that's what that means. And then, so that ensures that no other cores have cache copies of the memory location in a read-write state. So, it really ensures two things, because, if somebody else has access to reading, right, we want to make sure nobody else can, write during that time and, make our value stale again. So, these messages end in the active read-write epoch and begin a read-only epoch. So that's this transition that we saw up here, right? So going from core 1 being read-write and then transitioning to read-only when, say, cores 2 and 3 did a read. Okay, so then what's the other scenario? So if a core wants to write a memory location, right? So if they want to write a memory location, it has to send messages to other cores to get the latest value. So similarly, we need to make sure that somebody else is in a writer with a more recent value. And we need to make sure, kind of with the token example, we need to take their tokens away. And we need to collect the tokens from everybody, though. So we need to talk to everybody and make sure that all the read-write people know, hey, I'm taking your tokens now. I'm going to be the only person with read-write permission. And so you can't even have read-only permission. So these messages end any active read-write or read-only epoch. So if we go back up here, where's a good example of this? So in this case, right, so we have a read-only epoch right here. So cores 2 and 5 are read-only. Core 3 wants to write, but before it can write, it has to go to cores 2 and 5 and say, hey, what values do you have? Do you have the most recent value? If you do, let me take that from you. Oh, and by the way, you can't read that data anymore. And then we begin this read-write epoch. Okay, so that's basically how that works. Let's go ahead and continue. So, we'll talk about this in a lot more depth in later chapters. So let's talk about the granularity of coherence, right? So far we've kept it fairly vague, right? So we've just said some memory location A, and we've said for a particular location in memory. But what do we mean? Do we mean that, a specific bit has coherence tied to it? That'd be crazy, right? We don't want to maintain coherence for every single bit. Also, it's completely irrelevant. We don't work at the granularity of a single bit. So generally, loads happen, at the byte level. So they can range from being, 1 byte to 64 bytes. So, in theory, you could, at the finest granularity, you could have, coherence maintained for every single byte. But this doesn't really make that much sense, right? Because if you think about, what that would imply, that would imply that whenever we work or we did anything with a single byte of memory, that would mean we would have to generate a coherence request, right? And we'd have to generate something telling, hey, I want to read this value, or I want to write this value. And so it becomes infeasible at that low granularity, or that really fine granularity. But we also don't want to make it too big, right? So if we make it too big, it also really doesn't make sense, because then we could be lumping things together that don't need to be lumped in together. We'd be using a hammer for a problem that really requires a scalpel, and so this ties into this idea of false sharing. So while say if we did it at the granularity of a page, so a page in the CPU is normally 4 kilobytes. So let's say the first couple bytes want to be read by one core, and the last couple bytes want to be read by another core. Well, then we have an entire page that's having to be ping-ponged back and forth between two cores, and that really doesn't make sense. So what generally happens is we work at a cache block granularity. So this seems to be a good fit. It provides a happy medium between the two. Okay, so it's a little sidebar on memory consistency and coherence, but we'll go ahead and skip that, and we'll just start focusing on the scope of coherence. So, regardless of the definition we choose, coherence is going to have a specific scope, and we have to know what that scope entails if we're going to think about how it's implemented. So, what are the scoping issues? So, the scoping issues is coherence pertains to all storage structures that hold blocks from the shared address space. So this includes, the L1, the L2, the last level caches, and main memory. So these structures also include the L1 instruction cache and translation look-aside buffers, right? So fundamentally, instructions are just things stored in memory. So they're going to be reliant on that as well. And then also memory translations that we have in the TLB. So, coherence is something that deals with every single level because these values can exist at every single level. So we need to make sure they're valid at every single level. So the second thing is that coherence doesn't not pertain to the architecture. So it's not architecturally visible. So a system could be incoherent and still be correct if it adhered to the specified memory consistency model, right? So although this issue may seem like an intellectual curiosity, so, it's difficult to imagine a practical system that is consistent but not coherent, it has a highly important corollary. So that's that the memory consistency model places no explicit constraints on coherence or the protocol used to enforce it. So again, this is just driving home the fact that coherence isn't required for memory consistency. It's a tool. So how we implement coherence, we've got kind of a lot of wiggle room there in order to provide what consistency needs. So nonetheless, as discussed in chapters 3 and 5, consistency models, they may rely on certain common coherence properties for correctness. So, these things are linked pretty tightly in some respects. And so they may specifically rely on parts of a specific cache coherence process. Okay, so that's really going to do it for this section. So we really talked about cache coherence, what it means, and what the problems are. So as a brief recap, let's go over from the very beginning. So we started out, here's our baseline system that we're going to be going over for the rest of this book. So we'll have multiple cores, each of which has a private data cache and is all connected to a last level cache and main memory that's all shared. We saw that the problem occurs when we have values stored in our private L1 data cache, and when we have a write from one of the cores that's not visible to everybody. And so this is what we call incoherent. And so we move past kind of the hand-wavy definition of that looks wrong and is wrong to how do we define cache coherence, and we really define it by having a single writer and multiple readers, and having at the end of every epoch of read only or read write, it's data value invariant. So at the end of each epoch, the next epoch will have the most recent value. And then we talked about the granularity of coherence. So we talked about generally when we're doing cache coherence, if we make it too big, then we'll get this thing called false sharing. If we make it too small, we'll end up with just so many coherence requests, we're going to clog up our network. And then finally, we talked about the scope of coherence. So coherence is something that anywhere that data can be, we have to provide coherence at that spot. But we also talked about, how coherence, we'll reiterate this over and over. It's not a requirement for memory consistency, even though some protocols may rely on specific parts of coherence. But, coherence is a tool that's used to provide memory consistency. So that's going to go ahead and do it for this episode. We'll go into next time, we'll start talking about memory consistency motivation and sequential consistency. So we'll, really reintroduce what memory consistency is, as well as introduce a very intuitive form of consistency, which is sequential consistency. But that's going to do it for this episode. Check out all my other series I have on programming, GPU architecture, and a ton of other topics. My GitHub page is github.com/coffeebeforearch. You can check that out below. I put all the code that I use there. And as always, my name's Nick, and I hope you have a nice day.